Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss effects of positive feedback. Let's begin. In the previous video, we have already discussed about effects of negative feedback on input impedance, output impedance, gain, stability, distortion as well as noise. But in that particular video, we have to understand how positive feedback also responsible to affect all these factors. Let's discuss it one by one. For input impedance, how positive feedback affect. Consider an amplifier having gain capital A, feedback network with feedback fraction beta, input signal Vs, output signal at output voltage Vo across that of load resistance RL. Here positive end, negative end, from that of feedback network we obtain feedback voltage Vf, which is beta times of that of output voltage Vo. Since we consider the positive feedback, so V input is equal to signal voltage plus Vf, and at that of output voltage, that is A times of that of input voltage Vi. And its input impedance, let its input impedance as Zi, input current as I1. Similarly, output impedance Zo and output current I2. When there will be no such positive feedback, if positive feedback is applied, then that impedance will be changed, that impedance, input impedance changed to Zi prime and output impedance also changed to Zo prime. Let Zi, that is input impedance, of the amplifier without feedback. without feedback, whereas Zi prime is the input impedance of that of amplifier with positive feedback. Input impedance of the amplifier with positive feedback. So, input impedance Zi, that is voltage to that of current, input voltage Vi to that of input current I1, equation number 1. Zi dash, the input voltage at positive feedback, which is Vs to that of input voltage with that of feedback I1, equation number 2. From equation number 2, as Zi dash is equal to Vs divided by I1, or Zi dash is equal to, in place of Vs we can write, that is Vi minus Vf, Vi minus Vf divided by I1 is equal to Vi minus, in place of Vf we substitute beta V0 divided by I1 is equal to Vi minus beta, in place of V0 A times of Vi divided by I1 is equal to Vi taking common 1 minus A beta divided by I1, or Zi dash is equal to Vi divided by I1, this Zi whole into 1 minus A beta. As we know, 1 minus A beta, that value must be less than from that of 1. Therefore, that expression as Zi dash is less than Zi. What exactly it indicates? Here we confirmed the input impedance is decreased when we apply positive feedback by the positive feedback amplifier. Positive feedback in amplifier. Input impedance is decreased when positive feedback is applied. Next, what happened to that of output impedance? To calculate output impedance, we have to taken that a signal voltage as 0. To show signal voltage as 0, we have to short circuit that input section. Amplifier with gain A, signal voltage as 0, therefore that end is short circuited. feedback network, feedback fraction beta at the top outside, that load resistance is replaced by a voltage source. Output, the current as I2, here is the output, which is A times of that of input. Here Vf beta times of V0, here V input is equal to Vf as Vs is 0. Let Z0 at the output impedance, of the amplifier without feedback. And its prime is the output impedance with positive feedback. With positive feedback. Now we can apply Kirchhoff's voltage law to that of output circuit. Applying Kirchhoff's voltage law to the output circuit, we get the voltage V0, again here voltage minus I2, impedance Z0, I into R, that is V, minus voltage A Vi is equal to 0, or V0 is equal to I2 Z0 plus AVI, or I2 Z0 is equal to V0 minus AVI, as Vi is equal to Vf. Instead of Vi we can use Vf, or I2 Z0 is equal to V0 minus A into Vf, or I2 Z0 is equal to V0 minus A in place of Vf, that is beta times of V0. V0 as common, I2 Z0 taking V0 as common, 1 minus A beta, or V0 by I2. So Z0 is equal to V0 by I2, 1 minus A beta. V0 by I2, that is Z0 dash, 1 minus a beta or z0 dash is equal to z0 divided by 1 minus a beta. Which implies z0 dash is greater than z0. Why? As 1 minus a beta is less than 1. So we conclude the output impedance of the amplifier is increased by the positive feedback. When we apply positive feedback, the output impedance of that of amplifier increased. In this way, we show how positive feedback influence both input impedance as well as output impedance. Next, how gain is affected by that of positive feedback. As we know, the gain of positive feedback in amplifier, which is given by a dash is equal to a divided by 1 minus a beta, whereas a is the gain of the amplifier without feedback. As we know, the term 1 minus a beta is less than 1 in that of denominator section, less than 1. Therefore, a dash is greater than a dash is the gain with positive feedback, a is the gain without feedback. So we confirm, due to the application of positive feedback, the positive feedback increases the gain of an amplifier, increases the gain of an amplifier. When we apply positive feedback, then the gain of an amplifier is increased. Next, stability. Stability, basically we confirm it by taking stability of gain as well as circuit stability. To show stability of gain, when we apply positive feedback, so its gain as a dash is equal to a divided by 1 minus a beta. As we know, a dash depends on, from that of expression, a dash depends on gain A of the amplifier. Hence, a dash dependent of transistor parameters as well as frequency. Hence, the positive feedback creates instability of the gain in that of amplifier. The positive feedback creates instability of a gain in amplifier. So, with the application of positive feedback, the gain in amplifier is unstable. Next, circuit stability. As a dash is equal to a divided by 1 minus a beta, taking logarithm on both sides, log of a dash is equal to log of that term, and log of a by b, that is log a minus log b. Now differentiating both sides, log of a dash, that is 1 by a dash into d a dash divided by a dash. Differentiation of log a, 1 by a into d a divided by a. Here the differentiation of log of that term, 1 divided by 1 minus a beta, and differentiation of 1 minus a beta, as minus minus plus beta times dA. Next dA dash by A dash. Here we take the LCM A whole into 1 minus A beta. In that of numerator side, that is dA into 1 minus A beta plus A beta into dA. In that of numerator we take dA as common. Inside that of bracket we obtain 1 minus A beta plus A beta. A beta minus A beta cancelled out. So dA dash by A dash is equal to dA by A whole into 1 minus A beta. That dA by A is divided on that side. So we obtain dA dash by A dash whole divided by dA by A is equal to 1 divided by 1 minus A beta. That term is known as sensitivity. S stands for sensitivity. 1 divided by 1 minus A beta. Its reciprocal, which is called desensitivity. D is equal to 1 by S. D is equal to 1 minus A beta. As that term 1 minus A beta, as 1 minus A beta is less than 1, we can say that desensitivity is less than 1. From this we conclude the gain stability, here we confirm it, therefore the gain stability is decreased by the positive feedback. Gain stability is decreased by that of positive feedback. Hence, the circuit stability is also decreased. The circuit stability is also decreased when you apply positive feedback. In this way, the stability as stability of gain and circuit stability how influenced by that of positive feedback. Next, distortion. What is the distortion? If we take an amplifier, that is the amplifier, this is input, this is output. In that of input signal, if we take a large signal, so at output in that of amplified version we have non-linear distortion, means there will be such harmonic distortions. Why? Due to the voltage gain varies at different points of that of signal. How that distortion is affected when we apply positive feedback. Let we say V of D is the distortion output voltage of that of amplifier. So the output voltage is now changed to, that is the A times of Vi. A is the gain, Vi the input voltage plus the distortion output voltage. This is all total we call the output voltage of that of amplifier with distortion. In the presence of positive feedback, the input voltage is equal to the sum of signal voltage plus feedback voltage. But when we apply positive feedback, then what happens to that of output voltage? That output voltage is A Vi plus Vd. So in place of Vi we substitute Vs plus Vf Vd. In place of Vs, that is Vi times 1 minus A beta. In place of Vf, that is beta times of V0 dash. And simplifying it, A Vi whole into 1 minus A beta plus A beta Vo dash plus Vd. That A beta V0 dash now subtracted to V0 dash. Here we take V0 dash as common. Inside that bracket we obtain 1 minus A beta as usual that term. Next V0 dash is equal to 1 minus A beta is divided. We separating these two terms. So we obtain V0 dash is equal to A Vi plus Vd divided by 1 minus A beta. If we compare it to that of equation number 1, then we obtain Vd dash, which is called the distortion output voltage with positive feedback, will be Vd divided by 1 minus A beta. There will be a change to that of distortion voltage. What be that change? As we say, 1 minus A beta, which is less than 1, we called Vd dash now increased to that of Vd. Therefore, in case of non-linear distortion, when we apply positive feedback, the non-linear distortion is increased. Non-linear distortion is increased by applying positive feedback in an amplifier. Non-linear distortion increased by positive feedback in an amplifier. Next, how noise is affected? If we take V of n as the noise voltage at the input of the amplifier, then the output of that of amplifier without feedback, gain into the noise voltage. As we know, for that of positive feedback, its gain changed as A divided by 1 minus A beta. So by using that equation, we can write the expression for output noise voltage with positive feedback, V output noise with positive feedback is equal to VON, that is noise voltage at the input of that amplifier, divided by 1 minus A beta. As that particular term 1 minus A beta less than 1, therefore VON dash is greater than VON. So the output noise is increased by applying positive feedback in amplifier. Here output noise is increased by positive feedback in amplifier. So with the help of this video lecture, we understand effects of positive feedback on input impedance, output impedance, gain, stability of gain, as well as circuit stability, distortion, and finally noise. So with this useful and informative notes, let me wind up this session. Thank you.